Hey guys, this is Mr. Goya here. Hey, we're going to start a new unit today. This is Unit 9 called Momentum. Now, momentum is a word. Momentum is a word. Let me see if this thing's going to work here. Momentum is a word that we use a lot, especially in like sports, right? We might say, hey, that team has the momentum. So what does that really mean, that team has the momentum? Well, maybe they're doing really well. Maybe they just scored a touchdown, or they've shot some shots and made it. Maybe they're getting closer. Maybe the tide is kind of turned and now they're kind of up in the game, or they're maybe going really good and they might now win the game. In physics, momentum though has a real specific definition. In physics, momentum is the product of mass. So we take the mass of the object, that being kilograms, and we multiply that by the velocity, and that being meters per second. Okay, so it's m times v, momentum. M times v, mass times velocity. The mass then is in kilograms. The velocity then is in meters per second. So maybe we have then 1 kilogram mass moving at 1 meter per second. Okay, that would then have a momentum of 1 kilogram meter per second. Okay, that would be its momentum. Now notice an object has to be moving, right, for it to have a momentum. We could have a very large object, maybe we have a 100 kilogram object, but if the object has a velocity of 0, okay, it's going to have a momentum then of 0. All right, the object has to be moving. Where exactly does this idea come from? Well, it really comes from the second law, Newton's second law. So let me go ahead and change colors here. Second law, remember, is F equals not your pa, but your ma, ma. Well, we know the acceleration of an object is really the change of a velocity with respect to time. So what we're going to do is substitute. We're going to substitute this into that acceleration. All right, so a force equals to the mass times a change of velocity with respect to time. Okay, we can put the time on the other side, and that kind of gets me down to this equation here. Okay, we put the time on the other side, we get Ft equals to m delta v. That delta v stands for a final minus an initial. In this case, it's velocity. Okay, we use the distributive property here, and look what we have here. We have mv. There's that mv. Okay, that mv. There's that momentum. Okay, so look, we have a final momentum. Final momentum minus the initial momentum. Oops, is that going to work? There we go. Now, momentum is often given the symbol p, okay, small p. So final momentum minus initial momentum. We're saying that equals to Ft, all right? Now, momentum is a vector. We said we use arrows, right, to show ourselves vectors. A vector then has a direction, okay? We can use a grid for that, okay? A direction and an amount or a magnitude, okay? Let me kind of scroll down now, all right? So I'm going to hit my mouse here and just kind of scroll down here. Now this Ft, so we said then this is Ft, let me change my colors here. We said that this Ft equals to mv final minus mv initial. All right, well that Ft is given a special name too. It's called impulse. Okay, make sure this is going to work. It's called impulse, all right? So what we're saying is if we could then apply a push or pull, that's a force, right? Push or pull. If we could apply a push or pull and have that push or pull then be exerted on that object through a time, we can change then, or we can increase an object's momentum. Now, if this force is in line, if this force is kind of in line, thing's going to work here. If this force is kind of in line, okay, with the object, we can we can give that object a larger momentum. We see this a lot in sports, right? Tennis, baseball, softball, football, especially, we have then what's called the follow-through. What do we really mean by a follow-through? Well, with a follow-through, we want to keep that force on the object. So, for example, we want that bat to stay on that ball for a larger contact force. We want the tennis racket on that ball. All right. When we have follow-through, we can really increase that ball's or that object's momentum. Right. We can give a bigger final momentum to the object. All right. That makes sense. Okay. So we really wouldn't have to actually deal in sports. We could deal really with any object that we have a force, right? So in this case, we might have thrust. So we have an upward force thrust. And as long as that thrust is acting on the force, as long as that thrust is acting on the rocket through a time, okay, so in this case, this rocket engine's acting through time, we can then change an object's momentum. We can increase that object's momentum. Okay? So that kind of ends page 1. Okay, hey, so guys, I went on to page 2 here. Now, if the object is traveling, let me get all my pins here, get this working again here. If the object is actually traveling in one direction, and we want to stop that object, then we have to have a mismatch of our force and the velocity of the object, right? They have to be opposing direction. So we can actually take then our impulse momentum equation, that's what this is called, our impulse momentum equation. And if this force is actually negative, we can actually make the object get slower, or we can change the object's velocity so now it's less. So for example, we want to slow down that baseball, we have to apply a force in the opposite direction, and that force has to then, that force has to exist through a duration of time. All right? Now, this interplay of force and time, this whole idea of impulse, it's a product of force times time, right? And this whole interplay really is pretty important, especially when we talk about car safety and auto safety. So for example, there are really more than, there's lots of ways of stopping a car, right? If we want to stop a vehicle. Okay, we can hit a wall, okay, or something very hard, right? And that gives us a very small time, right? The car stopped in a very small time, but that leads to then a very large force. All right? Or we could stop the car. In this case, it's kind of a funny picture. We're driving that car through this big bale of kind of hay. The car still stops. We still changed its momentum, right? But now it takes a long time, okay, for that van here to get through the hay. So it makes this T larger, and because of that, the F has to be smaller. So we have a smaller force because we've made that time larger. All right? The product of Ft then is still the same. So this is still the same idea as this numerically, right? That idea makes sense? It's still the same numerically. But we would like to do this if possible, right? Because that then gives us smaller forces. If we have two, if our forces are too large, that can then really hurt people, all right? People can't survive if there's large forces on them. So for example, in cars, we build things into the car like airbags, safety belts, thing called crumple zones, and it increases time. It makes the car slow down and stop much longer in time. So we have a big T and we can then have a small f because we have such a larger time. Okay, I'm going to show you a quick little video now, and then I'll go on to page 3. We can do a real interesting impulse change of momentum experiment involving a couple of eggs here. What I've got here is this pie pan here, and I put this little kind of beanbag foam in that. As I drop the egg doesn't break. If I go from here, the egg broke, didn't it? Alright? So I'm dropping the egg from approximately the same height. In both cases, the egg has about the same velocity. With the beanbag, the egg then was able not to break, right? Because the change of velocity occurred through a longer period of time. That makes the force much less, all right? Without this beanbag, the egg had its momentum changed very, very quickly. That made for a very small time a very large force. With the beanbag, the time is much greater. It meant then the force was much less to change that egg's momentum.
Every car today comes with airbags, but what do the airbags come with? Mercedes-Benz earned a patent for the airbag in 1971. That means every airbag in today's Mercedes-Benz comes with 40 years of continuous innovation to make them smarter, more effective, and more protective. In the 1980s, the S-Class was the first car with a driver's front airbag standard. At the same time, a new emergency tensioning device, or ETD, was added to the front passenger's seatbelt. All of the restraints in a Mercedes-Benz are engineered to be most effective as a complete system. In the 1990s, Mercedes-Benz introduced the first side curtain airbags to cars and to SUVs. Since then, Mercedes-Benz has continued to lead the way in airbag innovations, such as separate pelvic airbags, head airbags for convertibles, and side curtains for the third row in SUVs. Even our original airbags have evolved many times. Today's front airbags feature dual-stage deployment, tailored to the severity of an impact. The groundbreaking pre-safe system can even sense a possible accident before it happens. Instantly, it can tighten the seatbelts, adjust the front passenger seat, and close the windows and sunroof. This helps prepare the airbags and other restraints to protect you better. When you subscribe to the Mercedes-Benz Embrace system, your car can automatically place a call for help if any of its airbags or ETDs are activated. After an accident, PostSafe also shuts off the fuel supply, switches on the hazard flashers, unlocks the doors, and turns on some cabin lights, all to help rescuers help you. The safety standards for all cars today include breakthroughs that were pioneered by Mercedes-Benz over the years. From airbags to anti-lock brakes, stability control, and far beyond, what starts here may someday make all cars safer. So when you think about airbags, think about something else too. The car they come with, and a history of innovation that's always put your safety first.
Okay guys, hey, we're now on page 3, and I've got some sample problems here on this page, and I thought I would do maybe a page of some practice problems for you, and then that can maybe help you in terms of working some of the problems on your own a little bit later. And again, I think you'll find it kind of helpful to have a calculator here with you. Now, the problems can be kind of general, fairly easy, or they can get a little bit more complicated. So at the in terms of the easiest type of problems that you'll have would be to maybe figure out the momentum of something. So momentum again is m times v. Okay, that's the momentum. It's again often given the symbol p. All right, so a question might say, what is the momentum of an object? In this case, it's this ball. So they give us the kilograms. All right, they give us then the velocity. Remember, mass has to be in kilograms. Velocity has to be in meters per second. So in terms of this, we can take this idea and multiply it by the velocity and get the momentum. For this case, we'd have 0.158 kilos. Multiply that by our 36 meters per second. That would be the object's momentum at that specific time. All right? Make sure that you can multiply these two and you get the answer that I've given you here. Okay? Now let's take a look at a problem like number 2. Okay, we have this 0.1 kilogram ball of dough. Okay, so that would be the mass. Okay, it's thrown straight up into the air. It has an initial speed of 18 meters per second. So that would be considered its initial velocity. All right. Well, when we throw an object up, what sort of type of motion is that? Well, it's in free fall upward, right? So we know when the object's velocity gets less and less and less. Finally, there's a point that the object stops, right? Its final velocity is 0. So it has an initial velocity, in this case it's 18, okay? And that velocity is going to get less and less and less as it goes up, all right? Now, so what's its momentum at the maximum height? Well, that's a pretty easy question, right? At the maximum height, we're at the apex, right? Velocity is 0, so the momentum is 0. Now, the second part of the question is a little more challenging. What is its momentum halfway to maximum height? So we want to figure out, we really need to figure out then how high the object goes. That'd be a delta x idea. We want to then figure out how fast is the ball traveling at half of that height, all right? Then we could find its momentum. So this one's a little bit more challenging. You know, we first really need to figure out, well, how high does the object go? Well, we aren't really given a time here. So what we could use is our equation, or we call it the timeless equation. Vf squared equals Vi squared plus 2a delta x. This delta x is going to be our unknown. Okay, we know the a is gravity, minus 9.8. We know the initial velocity is 18. We know the final velocity is 0. So we could say 0 equals then to 18 squared plus 2 times negative 9.8 times your delta x. We want to solve that for delta x, all right? So we square the 18, put it on the other side, then divide by negative 19.6, which is the product there. We can solve that for delta x. Okay, when we do that, then we get around 16.53 meters. Okay, so we know the object travels that far. Now, but we want to figure out then what's its momentum halfway. All right, so what we can do is take 1/2 of this delta x, all right, and that's going to be then half of that number. That's going to be around 8.2653. All right, so what we now need to do is figure out, well, how fast is it traveling at that specific location? So we can again use this timeless equation. Let me actually get another color here. Right, and so we can take then Vf squared equals Vi squared plus 2a delta x. Okay, we're going to put this 8.2653 in there, Our A again is negative 9.8. Our VI was 18. Okay, we want to solve this for VF squared, or VF really. So VF squared will be our 18 squared minus 2, or I should say really plus 2 times negative 9.8 times then this 8.2653. Let me make sure I'm going to stay on there. Push my calculator over a little bit here. So I have then 8.2653. I'm kind of running out of room there. And I want to solve this for V squared. All right, or VF squared. When I do that, I get to, what do I get? Around, about 144 or so. When I take the final velocity there, I take a square root, I get around 12.73. All right. Now, that doesn't really answer my question, but I'm getting pretty close. We want to get the momentum halfway. So the momentum again is mv. So we need to take this 12.73, the velocity times the mass. Well, the mass is 0.1. So I can move that decimal point over, and I get then an mv of around 1.273. And that's pretty close to what I've got for my answer here. All right. So that one's a little more challenging, okay, but definitely doable. All right, let me get my pen out here. So question number 3. Okay, what is the impulse needed to stop a 10 kilogram bowling ball moving at 4 meters per second? Okay, some key ideas here. It says impulse. Well, impulse we said was Ft. Okay, we said Ft then is mvf minus mvi, or the final momentum minus the initial momentum. All right? Well, we want to stop the bowling ball, so our final momentum would be 0. Our mass of our bowling ball is 10. Our initial velocity is 4. Okay, so we get negative 40. We get negative 40 here on the right side. Well, that equals then to my Ft. So that is my answer. What's my impulse? 40, negative 40. Okay, and again, this should be negative 40 for an answer there. So that equals to my answer. Okay, let's take a look maybe at question 4. A child bounces a 51 gram. Okay, there's the mass. Okay, but we need to put it in kilos. Okay, so that's going to be 0.051 kilos. Okay, that's the mass of the ball on the sidewalk. The velocity change of the super ball is from 25 meters per second downward to 12 meters per second upward. Let's draw ourselves a little picture here. Okay, pictures are good here. So the super ball is coming down. It hits the ground at 25 meters per second. That's downward. It pops back up at 12 meters per second. Okay, that's what super balls do, right? They hit the ground and then come back up. Now, it says the contact time with the sidewalk is 1/800th of a second. Okay, it doesn't stay in contact with the ground very long. It's fairly quick. All right, but it's not 0. The time's pretty small. Okay, so we want to get the force exerted on the super ball by the sidewalk. Again, we have Ft, that's our impulse, mv final minus mv initial. Okay, so we want to figure out what this force is. That's our unknown. Well, we know the time. It's 1/800th of a second. Okay, that equals to the mass, 0.051, okay, times the final velocity. Well, that's 12 meters per second upward, minus the mass times the initial velocity. That's 25 meters per second downward. Now, we have to be careful here. Downward is considered negative, so I have to put a negative in there. Do you see here? You have a negative and a negative. That's going to convert this into a positive quantity here. All right, we want to solve this for f. Right, so we want to take this times 12 plus this times 25. All right, then we want to multiply that by 800 to get the 800 on the other side, right? So we can solve this then for force. Okay, and when we do that then, depending on the rounding, you'll get approximately equal to around 1510 or so newtons, maybe a little bit shy of that. All right, be very careful. This is what we're saying, that velocities, momentum are vector quantities. You need to be concerned with the arrows in the direction. All right? Let's take a look at question number 5. It's definitely a little more challenging too. It says an animal rescue plane flying due east at 40 meters per second. Okay, so there's your velocity. Okay, drops a bale of hay from an altitude of 55 meters. Okay, there's your delta x or delta y. Okay, there it's given us the gravity 9.81. If the bale of hay weighs 169 newtons, what is the momentum of the bale the moment it strikes the ground? Okay, so do you remember kind of what's going on here? This is then a projectile. Okay, we call it a type 1, right? This is a type 1. So initially, this object, this plane, and then the bale of hay has a Vx. That Vx is 40. We said then that doesn't change, right? So right before the ground, it's going to have a velocity of 40. But once it leaves the plane, it's going to develop a downward velocity. Now what we have to do is combine these velocities. Okay, we're going to eventually use Pythagorean theorem, right? Does that make sense? We're going to combine those velocities, and what we'll need to do is come up with the Pythagorean theorem, right? That's the velocity we need right there, okay, to figure out the total momentum of the object. So we need to really figure out what this Vy is, okay? Well, we can get that Vy by the height. We know then the object is dropped from a height of 55 meters. So we can use Galileo's equations, or how far equation, delta x Vit plus 1/2 at squared. Okay, initially the bale has no vertical velocity, so that term goes away. This would be negative 55, okay, because it's falling 55. Notice I can solve this for t here. Okay, does that make sense? I can get the time. Okay, when I do that, when I do all the math here, when I get the time, I get about 3.35 seconds. All right. Now, then I can use my how fast equation. All right, we know the Vi again is 0. We have then negative 9.8 times that time, 3.35. Okay, we can get that Vy. Now that Vy is going to be negative, but that just means it's downward, right? So when I solve for that, Vy, I get then 32. What I get, 32.83. All right. So what I need to do to find this overall green, that green arrow, that hypotenuse, okay, I need to come up with the Pythagorean theorem. So I need to square this, add that to the square of this, take a square root, right? So when I do this, then I get this overall velocity. Okay, it looks like I'm running out of room, so I'll write it over there. I get the overall velocity then of around 51.75. So that represents my velocity of the object right before the object hits the ground. Now we want to get the momentum though, right? So we need to get the mass of the hay bale. Well, they give us then the weight of the hay bale is 169. So remember how to get weight equals then mg. So we can say 169 equals then m times your 9.81. Okay, you can solve that for mass. Okay, we get about 17.23. So that'd be in kilograms. So we take that number, m times your v. This times this, and again that should give you an answer of somewhere around 892, 891, somewhere around there. Make sure that it works for you. Now, the next part of this question again is based really on a type 1 trajectory. So we'd like to figure out this angle here. Do you see what the angle they're asking for? At what angle of inclination will the bell strike? Okay, so let me kind of do it with these colors here. There was that. And there was that. And there was that, right? So we want to get this theta right there. Well, that's opposite over adjacent, right? So you want to hit tangent, theta. In this case, you'd hit second tan. and you do your 32.83, divide that by your 40, and that'll get you your angle. Okay, again, make sure you're in degrees and not radians, so make sure your calculator's changed. All right, now the next problem is a little more challenging too. All right, and it's going to deal with a little bit of trig also. All right, now why don't you kind of read it? A 1 kilo steel ball, okay, that's the mass of the object. Okay, that's the m, strikes a wall with a speed of 13.5 at an angle of 44.8. Okay, so this is kind of the diagram of this. Okay, it bounces off with the same speed and angle. This is what's called an elastic collision. Okay, we'll study that here shortly in another day or so. Okay, so if the ball's in contact with the wall, okay, there's your time. What is the magnitude of the force, the average force? Okay, so get what that F is. They give us what the T is. Okay, there's the T. Okay, we know what the mass is. It's 1 kilo. So we know what the mass is. 1 kilo. 1 kilo. Now, here's where we have to be kind of careful here. All right, so let me grab another color here. So what we've got really here is part of the velocity is velocity along the x direction. Part of the velocity is velocity in the y direction. It hits the wall and then bounces at this angle. Okay, again, part of that velocity is in the y direction. Part of it's in the x direction. Now, notice then that these vy's are lined up. Okay, so after it hits the wall, it has the same velocity vertically as it did initially. So consequently, we don't need to discuss this with our momentum calculation, okay, because these cancel out. What we do have to deal with this is this Vx. So it's going this way, and then it rebounds the other way. So we're going to have to get direction associated with this. So this Vx really then is, so if this is my angle there, there's my angle, same angle. This Vx is really then this cosine theta component. So if we know the speed is 13.5, that's my hypotenuse, right? So I'm going to take 13.5 times the cosine of 44.8. All right, can you do that? Make sure you can do that in your calculator. Well, when you get that, you'll get then a Vx of about 9.58. Okay, does that idea make sense? Now it's going to the right here, and here it's going to the left. So I'm going to call this positive 9.58. This will be minus 9.58. All right, so my final velocity then here, is negative 9.58. My initial velocity is positive 9.58. Okay, so we know then mass, final velocity, mass, initial velocity. We know the time. We can solve this for F. All right. Now, when we do the calculation, we get like a negative 73.97. Okay, but the question then asks for the magnitude. Magnitude, remember, is just an absolute value. So we want to convert that into an absolute value. So you should get somewhere around maybe 74 newtons or so, depending on your rounding. All right. Now, so this page here has a lot of practice problems here. These are problems you'll probably see kind of on the online homework or in some of the other practice problems that we do. Okay. Momentum, again, is m times v. All right. Sometimes figuring out the velocity is not so straightforward. Sometimes they give you the velocity, sometimes you have to calculate the velocity. Sometimes the object's in free fall, sometimes it's moving as a projectile. So this takes in a lot of the concepts that we learned last unit. Sometimes we have to use a little bit of trig to kind of help us also. All right? That ends page 3. We'll talk to you later, kids. Bye.